Let's start our meeting today and continue with the second lecture of Nikolai Vovchanskii, devoted to applications of fractional step method Okay, please.
Thank you. The plan for today's lecture is to go for some kind of a journey. We start with the standard application of the splitting procedure to the semigroup associated with the SDE. Then we move towards the situation where some specific stochastic properties are investigated and used and exploited. And in the end, we will face a somewhat exotic situation of a coalescing stochastic flow where a specific metric should be used to measure the speed of convergence. And this part should serve as an illustration that in general, you can use the same idea of splitting, but you need to tailor your tools and your methods to accommodate for a specific problem you are facing. And this last part is going to include results obtained by myself and Professor Drogovtsev in cooperation. So this is the plan. And let's start with a brief recollection of what we have achieved last time. So we have the Cauchy problem, abstract Cauchy problem that is just a PDE. d over dt of u equals the sum of two operators, unbounded, so for instance, some kind of derivatives. We know that at time t, our solution equals to some function u. And if these ik are good enough in the sense that generate continuous semigroups, strongly continuous semigroups, akt t is greater than 0, then the solution to the initial problem can be reconstructed by using this procedure. So by considering some problems, composing them in a specific order and using them on the initial data. And this is a particular example of the procedure of splitting, where you start with the problem, decompose the driving force or the mechanism that describes the dynamical system into smaller pieces that are more treatable in some sense, and you solve some problems, and still you are able to recover the original solution. So this is the Trotter-Lie-Kato formula. Split the method of splitting, the method of fractional steps. Now let's consider semigroups associated. I will provide a proper reference in the end of this section. However, I will mostly follow the exposure of the paper of Ervan Fao. I don't know how to pronounce usually surnames, so I'm going to butcher almost every surname I meet. And I apologize for that in advance. We consider a simplified version of the problem. So just consider a standard heat equation plus some free term uxt. So ux u0 is u0 and t lives in this time interval. Now, these are problems The first one is the heat semigroup. I will denote a solution of it as this is a notation, and this is just Wxt. I will denote the solution of this ordinary differential equation, phi of t of w of x. In this example, we will follow a method of obtaining the speed of convergence and proving the convergence simultaneously that we discussed last time. That is stability plus consistency imply convergence. That is, so stability means that the application of subproblems do not propagate an error. So this means boundness in the terms of the initial data. And consistency means the following. By SH, I will always denote the one step of our splitting procedure. That is, this is the composition of two operators. In our case, this is going phi t of H. So first we solve the heat semigroup, then we use the solution to the ODE. And we want to have something like that. In a proper norm, this should be less than h to the power of 1 plus epsilon. And then we will estimate the error of the whole procedure by using this simple algebraic relation, where these terms will be estimated because of stability of the method, assuming it holds. It is true that the method is stable, and this will be estimated due to consistency. Let us use and recall the Feynman-Katz formula, since we will need it also later. I will formulate it in the homogeneous with respect to time case. So this is Feynman, a well-known Feynman-Katz formula. And it states that if you have, I will recall it in general case. You have a PDE with potential V, then the solution can be and V is bounded, or for instance, bounded from above, or just bounded, and or then the solution can be obtained as follows. Ts, where psi x of t is a solution to the corresponding stochastic differential equation, starting at x, at time 0. In our case, psi x of t is just x plus wt. And okay, so let's move to splitting So we will use the following version. So this is FH U0 plus WH. And we will consider the case where this initial free term is just a multiplication operator. In this case, one can just solve it directly, explicitly. So this is one step of our splitting. And this we immediately have the stability because this is a contraction semigroup and this is also a controllable thing. And then one can prove the following result, that actually for any p then greater than 1, including this SHU0 of x minus UHX understood as a function of x in the corresponding is less than some constant h to the power 3/2, and we have the corresponding norm of E0. Let's say just one thing about the proof, and the proof is actually going to use this Feynman-Class formula, that is x plus wt. Here is going to be the difference of two exponentials. The first exponential is the integral of this form, and the second is just, I'm sorry, here I should stand h of x, and one can I'm sorry, and here is going to be integral from 0 to h of this difference ds, and then you need to impose some conditions on v, that is, it is Lipschitz continuous, to proceed further and to obtain this result. And of course, this immediately implies, as we told, that one can recover, I'm sorry, the original solution if Hn equals t to the power n u0. This is less than some constant h to the power of 1/2. And we also last time discussed the strength splitting, the symmetrized version of the scheme. In this case, it's actually going to have the same order. And a linear case can be also treated using the same approach. However, this will require V to become even smoother, more regular. And this is the general principle, that to obtain something, we need to, some estimate, we need to take V smooth enough.
I'm sorry, I have a question.
Yes.
You said that stability plus splitting implies convergence, yes?
No,
And,
I didn't say that. I said stability plus consistency.
Consistency, yes, yes, I'm sorry. Yes, it's imply convergence. And in this convergence, in what sense? Weak convergence or in probability?
This sense.
Here. In this sense,
in
yes.
This sense, yes.
In this sense, yes.
Mm-hmm.
It's not probability measures convergence, yes?
No.
No.
This is just a convergence type of semi-groups generated by those PDs. We will see.
So we know semi-graph technique is is used for example, there is a book from either course, yes, in Markov chains, and yes. Thank you. Yes. Thank you.
You're welcome. So yes, for such theoretical results in group techniques is supposed to work well in many cases, but not always. And to finish this example, I want to show splitting and the Feynman-Katz formula, since physicists like to prove the Feynman-Katz formula using splitting. So again, we will consider the same, essentially, PDE. This is called the Schrodinger equation, so it describes the wave function in this setting. And again, let us write one step of our splitting. This is h e of x integral this over r or rd in general, dy1, and here stands the Gaussian density with mean x and identity matrix, sorry, h times identity. Now, if we do this enough, repeat this step enough times, we will end actually with the following expression: dy1 dyn gh xyn from 0 to n minus 1 gh k yk plus plus 1 from 1 to n, yes, phi of y1, and here stands exponent minus minus h, the sum from k from 0 to n minus 1, v of x plus, sorry, there is no x, there is just y k plus k1, yes, and also there is minus h v of x. And of course, under pretty mild assumption, with this converges immediately to what you would expect after rearranging the changing the order of these integrals. Yes, this is, I think, a nice example. And now we are going to switch to the next example, which actually considers the SDE. However, it delivers an example of the situation where the estimate of the speed of convergence, now the convergence is considered not in this strong sense, but in weaker sense of LP convergences of processes. So SD is LP convergence. Now we are not dealing with good semigroups anymore. So we consider the SD of this form. I will write it in this form. DWT x of 0 interval. And coefficients are supposed to be as smooth as we need, so the ellipse is continuous in x, they are continuous in t, they are of linear growth at most. let me introduce some notation hn, or I will drop usually n, because we will consider one step and we will consider all steps simultaneously only when passing to the limit as the very last stage. This is t divided n plus 1. Then one can define yk, this is kh, k plus 1h. So this is one step of our splitting procedure. And then the scheme works as follows. We consider approximation on the nth step, then we introduce new additional auxiliary step, and then we provide the estimate on the next step. And on this ik, the case interval, it runs effectively as follows. KHT. I will also introduce some notation an of t. This is a of t, un of t, and bn of t. This is b when we substitute here this function. An of s ds equals yn, and here so it's a very standard splitting scheme. KHT bn of s dws. And then the output of our algorithm, that x of t capital is yn plus 1 n at times n plus 1 times h minus. This is the limit to the left. It is important to have the another representation, which might be very helpful in many cases. For that, we will need additional notation that if we have some t, it belongs to some ik. So here our t is some ik, there is kh, k plus 1h. We will denote this dt, and we will denote this dn of t.
Colleague, excuse me, may I ask a question?
Yes.
So bn depends on yn of t. So this is equation for yn. It is not integral.
Yes, this is equation.
Okay, thank you. So I see.
So yes, it should be solved in this sense. So yes, effectively we have two SDs. The first one is degenerated in the sense it doesn't contain a stochastic term. So this representation, it actually becomes very clear how it looks like. So this is the starting point. dws and yn of t. Here we integrate to the end of the corresponding interval. dt bns of s dws. And let's speak briefly about how we are going to obtain the convergence we seek, because it provides an interesting perspective. So using the Ito formula, one can establish the following result, actually. Sorry, S ds and a counterpart for y. This is going to have t is the same integrand. This is going to equal the very same thing, but the integral is going to be from 0 to t. It's pretty clear how to prove this. You use the E2 formula on every interval and just sum them up and add what happens on the very last interval where our t lives. And this estimate proves to be an important result for obtaining stability and consistency. So the proposition, I'm sorry, I will need to consult notes to be consistent. Plus t is actually bounded just, which immediately results in the following bound, for instance, and the same for y, and squared is less than c, actually n minus 1. What is important here that all constants, I will usually use the same letter for all constants. They do not depend on anything important in the sense they do not depend on t. Also, we have here just the first order. So we need to do something to prove the convergence. I want to give one comment on the proof, that to prove this, using this relation, one actually uses something like this. X of t is less than c1 plus c2 x squared, where c1 and c2 is greater than 0. And this is one version of the cursivity condition. And this is for a reason, as we will see in a moment. And this is a useful relation that after introducing it into this formula and using the Grover-Bellman inequality allows us to prove this estimate. And now we're almost ready to speak about how the resulting convergence is obtained. Because one can write, using this second representation of the splitting scheme, in the following form. Everything may be rewritten in the following form.
I have one more question.
Yes.
Do we need some smoothness of A with respect to T parameter?
Yes, it's continuous. I think it is enough to have just continuous.
Mm-hmm. Okay, thank you.
You're welcome. So effectively, I'm writing A, and the authors of the paper, I will mention it in a moment, are writing them in the left-hand side, because when you prove all these estimates, it is convenient to collect everything together by just canceling the appropriate terms that appear in the left-hand side and in the right-hand side. So this is for convenience, and also because it's customary in the field they are working to. We have this representation where alpha n of t is actually minus integral d n of tt. This is a stochastic correction. And this is a deterministic correction. And looking at these two integrals, it is expected that we might get something like this. Some constant times h, because we integrate over the intervals which length is no more than h. Okay, so okay, so we have discussed enough to state the main result, which says that under all these conditions, converge to the solution of the corresponding stochastic differential equation in L2, just in L2. We are not speaking about the semigroups associated with this equation. So this is also the illustration for the first question I got. Now we are, in some sense, we are getting stronger convergence, in some sense. But also we have convergence in L2 in this sense. Speaking about the proof, let us speak very so here one way to get this result is to say that UN and U are bounded in this Hilbert space. Then by the Banach-Haloğlu theorem, they are relatively compact, so they have a limit. There exist limits. And then one needs to identify those limits, which can be done by passing to the limit in this stochastic differential equation and this stochastic differential equation. Another way maybe to add additional step where one just proves that this is a Cauchy sequence. And then one gets a strong limit in contrast to the first way where a weak limit is obtained. And now let me go to the references, because what we discussed here, the first reference is OU. We already talked about this. And this example is a sketch of what these two papers achieved. And since it is written here stochastic evolution equation, this actually means that both these papers deal not with the ordinary stochastic differential equation, but the stochastic partial differential equation. That's why this relation that I named a cursivity relation makes a great sense in those settings, because it's really a cursivity of the appropriate operators. And these papers actually deal with different problems. The first paper proves the convergence and establishes estimates. The second pair of Goncharuk and Kotelenets actually establishes the existence of the solution by using this splitting method. So they construct the solution as the limit and identify it as a solution to the corresponding SPDE. They do not know in advance whether this SPDE exists, has a solution, the unique solution, or not. Moreover, they use it to establish the comparison theorem in case when everything happens in R. And it's quite easy to see that if the drift, this is, if you consider the initial d x of t, oh, I'm sorry, d t plus some sigma x of t dwt. If you consider this ordinary stochastic differential equation, one can prove, assuming that A is at least locally Lipschitz, the comparison theorem using the splitting method. This may be an exercise. This is because we can, on ODE step, we use the comparison theorem for ODE's ordinary differential equation, and we have an appropriate monotonicity due to the existence of the unique solution on the stochastic step, part of the step, the stochastic part of the step. And again, we see that for this method to work, we need A to be smooth. And we know that the general comparison theorems of stochastic differential equation works for very bad drifts if they have some relation between them, so that you can put two continuous functions in between of them such that a strict inequality holds. However, in the setting discussed here, this is a highly non-trivial result. And also, I want to mention that this is a continuation of the work on Daletsky and Goncharuk, and this is an honorable mention because in terms of SPDEs, the Gelfand triple that is considered by Goncharuk and Kotelyanis is a continuation of the work started by Daletsky and Goncharuk. And I also need to mention that last time we discussed terminology and said that Daletsky did some work in this direction. And I've known about this paper for years now, but it wasn't until like a couple of days ago that I understand that this is not Daletsky. This is Daletsky. Daletsky. And again, for those who is interested in the topic, I can recommend the paper of Gyöngy and Krylov on the same application, but they use a different method. And also we mentioned the proof of the famous Katz formula via splitting. And one can also prove the Girsanov theorem, a simplified version of Girsanov theorem for, again, regular drift using also splitting. And one can find the proof in this paper. And also on terminology, as you see, people sometimes use splitting up instead of splitting. I have no clue why, but this happens. So we started with a standard semigroup approach, and then we switched to something that is purely stochastic in its essence. Though, of course, SPDs follow the framework of variational solutions. Now we want to consider a specific example of a very different setting. So we want to consider Brownian web with drift. I think the erratic flow was already mentioned on these readings by Ekaterina Glinina. So we are dealing with a very similar object. We have a family. And this is a family of coalescing Wiener processes in the sense that for any U1, UN, for any T1, Tn, BT1 as a function of the second time variable, time argument, are coalescing Wiener processes. This started at time T1 from point U1, at time Tn from point Un. So on a picture, it looks something like this. So this is T1, suppose this is T2, T3, this is U3, this is U1, and this is U2, and we have Wiener process that move, and they are independent before they meet, and once they meet, they match together and move as again as a standard Wiener process. Simultaneously, one can speak about such system, which is called a stochastic flow, when those coalescing Wiener processes are correlated before they meet. And if the correlation function is smooth enough, they can actually be obtained a solution to the corresponding SPDEs. So in some sense, that case is treated in the previous papers we discussed. However, there is an trivial result that Such system of coalescing linear process, because they are, cannot be obtained as a solution to a good SPD, to a solution to SPD, because they are independent. This independence prohibits that. That means that this is a situation that requires another tools, and in fact, it requires another approach. So again, we want to construct a system where particles again move as linear processes, however, with drift, again independently, and again they merge. So we want now to construct a system XA, also indexed with two time parameters, in the sense that for every particle, this is some linear process, plus A U dt, and this particle starts at time s from U. We will suppose this is a Lipschitz function and it is bounded also. If we look at the original formulation, we can associate with the flow a family of mappings. This is not a continuous mapping. This is a Cadillac. There is a modification of the flow, that this is a Cadillac function. And this holds for every S and T. So in some sense, we can now consider this is the first subproblem, the first driving force, just as the Brownian web. And we can consider the ordinary differential equation. And this again provides second subproblem. So despite the fact we are not dealing with semigroups, we can use the same idea of splitting, however, in a very different realization. And now this is, again, recall that AK, this is KH and K plus 1 HN. By HN, I will denote the terminal time divided by the number of steps at this iteration, at this iteration. And on IK, this is BKH of T composition, J from 1 to K minus 1, B minus 1, H, JH, again composition AH, and this all defines a function from U. So on a picture, here our particles moves as if it were transported by the Brownian web, ordinary Brownian web. Here it is a solution of the SD, and we repeat. And then we throw away all these components and we obtain a discontinuous function. If we are interested only in convergence, we can use the same idea that appeared at the very last step of the previous example. In the sense, if we consider a finite number of particles and we consider a function T U1 xnt m is the number of particles. So this is a function. This belongs to the Skorokhod space with the product topology. And again, we can show, because every xn is actually Brownian pieces of a Brownian motion that are shifted by some controllable jumps. And of course, A of S is a very controllable thing. Therefore, one can check that this vector, I can denote it psi n is a weakly compact sequence. And since it's weakly compact, it has limits, and one can identify after some calculations the limit and prove that the limit is indeed a subsystem taken from the Brownian Weber's drift. However, this is just a convergence result, and one can ask what is the proper way to measure the speed of convergence. In some sense, this is ongoing work, but the result that has been established by me and Professor Bergovtsev some time ago is as follows, and it's closely related to the previous lectures given by Ekaterina Glinina, where she told us about point processes associated with stochastic flows. So indeed, we can consider the push forward measures in the following sense. We have this flow XA or XN, and we have some distribution of the mass at time 0. Then we can ask how this measure is transported by the flow. What is the distribution of this measure at time t? And for that, one defines, we will consider just the case of the Lebesgue measure. So when this is just a flat surface, t to the power -1 and mu n of t. This is a forward of the Lebesgue measure under the action of the corresponding flows. In the sense that, for instance, mu a of t of delta, this is the Lebesgue measure of all points such that their positions at time t are inside delta. So of course, both these flows are coalescing. So we have here some point process. So as we are measuring not only the number of points that got into some delta, but also the value of the cluster that is represented by a particle. So we have clusters here due to coalescence, and all particles inside of this cluster have coalesced, have merged before time t, and we also ask in the question how many of them in terms of the regional measure. And to measure the distance, standard way is to use the Wasserstein distance. So suppose that P2 is the space of all probability measures on the real line with finer second orders. So for every mu belonging to P2, there exists a random maybe defined an appropriate probability space, a random variable such that mu, the law, the distribution of psi is equal to me, and the mathematical expectation of the square of psi is finite. And then one defines the distance between two measures as the infimum of all possible realization of a pair of random variables such that psi k has distribution mu k of just a distance between those two random variables. So this is effectively the norm in L2 omega. Such metric is closely related to the so-called transportation problem, which again is what we have here, in the sense that if we have some distribution of a mass, a logistic problem of moving them into a new configuration, we want to minimize the cost of this transportation. And we suppose that the price for moving one piece into a new position is proportional to the square of the distance between these two positions. So this is a very standard tool. However, these measures mu a and mu n are random. So we need one additional step, because we need to introduce the distribution of this random measure. We need to introduce the distribution of this random measure. And they both live in the space of measures over the space of measures. And here we introduce a metric in the very same manner. We just use all possible random measures as the distribution of mu k is given by this L capital K, and here we use the previously defined distance, the sustained distance. However, this is a random, so this is the second step. So now to attack the whole problem, one follows the plan. So one obtains of particles. Because when you consider just one particle, this is essentially an ordinary splitting for one-dimensional SD. It has been covered before. Then one built simpler random measures. Then one construct those measures for mu at and mu nt simultaneously on the same probability space. And the second step is, of course, gather everything together. Gather everything together. So to formulate some auxiliary results, I will introduce a couple of notations. So if you have this SD, I will write that X is D of W X0. So 0 is the starting point. And if there is a splitting for this expression, so this SD, so this is ODE part, and this is stochastic part. Then I will encode this by writing this is splitting, maybe just S, 1 over N, this W x0. However, in general, we will need, oh, okay. And then one can prove something that is very similar to the examples we considered before. If we keep two solutions and theta is the meeting time, then the distance between these solutions squared is actually less than where D of A is a mixture of L1 and L2 norms. However, this is the first proposition. This second proposition considers the splitting over the time interval of length 1 over n with some Wiener process. However, we also allow some disturbances at the beginning. So we start those two splitting processes not from just one x0, but we allow them to be different mechanically. And then theta n is the meeting time for y's, the meeting time for y's. It is general and open question which part of the splitting procedure you use to approximate the function. It depends in general, from what I saw. And this one can prove this holds for any epsilon less than 1/2. This term is actually not of a big problem, not a big problem. And effectively, these two propositions say that if in our flows, the limit one with drift and the pre-limit one, two particles start close, they stay close. And then they meet and nothing bad happens. And this is the reason why in the second step we can replace mu-a-n and mu-n-t with a simpler discrete measures of the following form. So we just do not need to consider the movement of all particles on the interval 0, 1. Maybe I forgot to mention that we consider the Lebesgue measure only on the finite interval. And this is just the delta measure that catches the position of the particles that starts from Km. And the same here. This is by definition 1 over m x and Km. It is sufficient to estimate the distance between these two random measures. And for that, one applies the following idea. So if we are given standard independent Wiener processes, we can construct, there are m of them, we can construct coalescing Wiener processes. However, well, wait. Then we can construct the solutions as these dt plus dwk. They're independent, so x's are also independent. And then we can construct a coalescing system by merging them together when they meet in some. We just need to ensure that we always, when two particles meet, we always allow to survive the one that is higher, that came from a higher region. So now they are coalescing. And of course, this is what happens in the limit flow. However, simultaneously, we could construct a sequence of splittings, UN, with some starting points, x0, k, x0, k from 1 to m. And we should construct actually specifically by using the coalescing moments of this part of the splitting procedure. I will not go in the details, but I just want to say that this coalescing linear process is not what happens if we consider something like merging by force the original ones. This will result in some additional errors for what this proposition is aimed to accommodate for. And if one gathers everything together and does some tedious computations, but pretty straightforward, one can prove effectively an abysmally awful rate of convergence. So this is smaller than iterated logarithm to the power 1/2. One logarithm, at least, is the result of the method chosen to prove this main result. It might be possible to eliminate at least one logarithm, but this is work in progress in some sense. So this part is actually an abstract of these two papers. And I also want to name a couple of general texts. If someone gets interested, one can use almost any textbook on the semigroup theory to get full proof of the standard version of the Trotter-Lie-Kato formula. I just named two of textbooks, but there are much more out there, and you can take whatever you prefer. And also, I named here three textbooks, or maybe not texts, but monographs that deal with splitting methods specifically and describes current development in this field, mostly from the numerical point of view. However, this also contains results on the convergence, rigorous results. They all contain rigorous results, but they mostly aimed at numerical methods. And that's all I wanted to tell you.
Okay, thank you very much for interesting lecture. Maybe somebody have questions, please.
I have a question about the last formula about convergence. So does it mean that L and T, this approximation, converge in some strong sense, I mean in probabilistic sense, to LA of T?
Well, the state distance effectively is equivalent to the weak convergence.
But you see, so does this imply convergence of approximations for Brownian web?
I don't think so. So at least it doesn't strike me as an immediate fact.
So we have convergence of measure valued processes, but
Yes.
not webs.
So I do not know the answer. So as of now, I do not know whether this is true or not. One aim of the project I'm trying to work right now is to answer this question, to understand whether this is enough or not.
Thank you.
You're welcome.
Okay, other questions, please? If there are no any questions, then we thank our speaker again for presentation of interesting material, and we will meet at next Tuesday. Maybe Katerina, do you know who will be next speaker?
Yes, one moment, please. I will find it.
And while Katerina is searching, I want to thank you, the participants, for the possibility to deliver this talk. Thank you very much.
Thank you.
A moment. So the next one moment, please. So the next will be Andrei Anatolyevich Dorogovtsev with talk equations with interaction and Markov evolutionary processes.
Oh, okay, this is good memorizing for me too. Thank you. Okay, see you next week.
Okay.
Bye.
Bye. Bye.
Thank you.
Thank you.